Okay, good morning. Uh, Continue our discussion about the use of the switching power pole, and let's try to understand how to use heat for, say, converters to build up converters for DC motors. Let me just put here the adjective bidirectional converter for DC motors. In order to illustrate these bidirectional converters for driving direct current motors, let's start with an example. Suppose that you have this circuit, and in this circuit you have the switching power pole. Let me just draw the switching power pole by using the bipositional switch. So 1 and 0, and this is the A node, N node, this is LA, for example, this is CD. At the voltage port, you have the voltage VD, which is a constant voltage, okay? And at the node A, the current port, you have the current IA flowing here. Okay, then you have also the unitary switching function QA, logical signal that drives the position of this switch. Okay, so here at the output, just put the electrical equivalent model for the DC motor, and this is made by say, basically you have here a model which is made up by inductance modeling, say, the magnetic flux linkage of the winding of the motor. And then you have the, say, ohmic losses represented by the resistance R. And remember that you have the what is called the back EMF. Okay, this is, let's say, a EA, for example. The back EMF is something which is proportional to the rotational speed of the motor. Okay, we studied the way to models the input, the supply port of a DC motor previously in the lecture, okay, devoted for just students in electronics. Students in mechatronics, I think that they already know, say, models like these for DC motors. Okay, so basically the inductance LA and L that are in series can be represented by just a single inductance. Okay, so let me put here just the inductance LA. That can be simply the inductance of the motor. Okay, LA can be exactly the inductance of the motor, or maybe it's say the summation of say two inductance. But by the way, the DC motor can be represented at the input electrical port exactly in this way. Okay, so suppose that we are in steady state, so we can analyze this circuit for steady state operation. Steady state operation means that you have no transient, and so that means, for example, that omega m, the rotational speed of the motor, is constant. And so if this is constant, the back EMF, this is the back EMF, is also constant. Okay, so we have a battery that is not changing because omega m is constant. Supposing that Vd is constant and the value is 100 volt, the back EMF constant voltage is 75 volt. Ra, modeling the ohmic losses in the winding of the DC motor, is 0.5 ohm. La, the inductance of the motor, basically, this is 1 millihenry. Also suppose that the switch is operated at in a periodic way using a frequency of the switching which is 20 kilohertz. Okay. So for that circuit, I like to consider two different situations. Okay. So let's consider two cases. Let me call the first one A, that in which the average current flowing at the current port is positive with a value of 5 amp. And in the case B, a current average at the current port which is negative 5 amp. So for these two different situations, so this is the first question, compute the average value of the voltage at the node AN at the current port and the duty cycle for the cases A and B. The second question is to evaluate the current ripple, but only for case A, oh my god, which here's the current ripple of IAT, and 3 for the same case, for the case A, which is the maximum available ripple of IAT. Let me call that this is not necessary, okay, which is the maximum available ripple of IAT. Okay, 3 questions. Let's start with the number 1. So we have to compute the average value at the voltage port, and also we have to compute the duty cycle. Let me just answer the question. Can you show again case A and B? Of course, I just say go into the first page here. The case A are, say, two different currents. Okay, IA average current is 5 amp, IA average current negative 5 amp. So let me consider how to compute the average value. Okay. The average value of the voltage VIN is a, let's say, DC quantity. Okay, because it's something that is, say, constant. Okay. What is the expression? So just something that we learned from previous lecture. Let me just consider the waveform of the voltage VIN at the current port, this is something like this. I don't know the duty cycle because this is something that we have to compute, but I know that depending on the position of the switch, we can have that VIN is the same of VD during, let's say, this time interval, T on, or it can be 0. Okay, so this is the variation of the voltage VIN that we have here. Okay, when the switch is in the position 1 is VD, when the switch is in position 0, this is 0. The average value of this quantity is, for example, at this level, okay, and the average value is always due to the product of the duty cycle multiplied VD. Okay? You can decompose this quantity into the summation of two different quantities. The first one is a, say, constant quantity, which is the average value, VIN average value, which is exactly this level here. Okay, plus a contribution that is just an AC component of the voltage VIN. So it is the voltage VIN minus the average value. And this is something okay. So this is the first one, the DC average value is just a DC part, and this is just a, say, AC part. So here, no DC component is present, okay? So this is just AC, just the variation. Okay, the summation of the two gives you exactly VIN T. Okay, so here, basically the area here should be the same as this one. Maybe the drawing is not correct. Try to do the best to have this quantity to be the same. But anyway, the concept is that I can separate the two parts. Okay, just the DC part, no AC contribution, and then AC contribution, no DC, no DC part. So in this sense, I can say replace all this part here, which is basically the switching power pole with the CD and the bipositional switch, by using the equivalent principle. Okay, so just use, we have the node A, the node N, then we have LA, RA, and the back EMF that represents the DC motor model here. And here just put VAN plus its average value. Okay, this part here is just the AC contribution. Let me call correctly. Let me put the summation of DC and IC in this way, with capital letter here. And this quantity here is VAN small letters, okay? So VAN here is just the AC part. So the summation of the two provides VAN. Okay, this is the same circuits, okay, in which I replace basically the switching power pole with the voltage that appearing at the node AN, okay, and then this is connected to the DC motor model Okay, so we can use the DC average value for computing DC quantity in our circuits. Okay, the DC quantity means to compute average quantities, while the AC part, okay, can be employed for computing just the AC electrical quantities, for example, the ripple. So in this sense, I'm using a sort of superposition problem, superposition principle. Okay, I separate DC contribution and AC contribution to separate my computation. So let's start by computing average voltage, average quantities. Okay, in order to do that, from these circuits that includes both DC plus AC quantities, okay, I can say just consider applying a sort of a superposition principle the DC contribution. Okay, so just consider DC electrical quantities, because I'm going to compute average quantities. Okay, so I need DC electrons. The circuit is something like this. This contribution is no more, say, to be considered in the DC contribution, because this is only AC. Okay, I have to consider just the average value. So VAN average. What about RA and EA? Okay, RA must be considered, and also EA is a constant. Remember, we are in steady state, so we have to consider it because it is in a DC electrical quantity. What about the inductance? We are in steady state. The inductance in steady state, say, is as a voltage across it, the average voltage across the inductance, which is null. Okay, so in steady state, the inductance is a short circuit. So this is the basic circuit I have for computing DC electrical quantities. Let me just put the current here flowing in this overall circuit. The current is a current IA, which can be considered as the summation, again, as we did for the voltage VAN. We can separate the DC contribution and AC contribution also in the current IA. So it is the summation of the average quantities, DC, plus IA, which is the contribution, which is totally AC. So here in this circuit, I have just the average value. And so which is the average value of the current IA is VAN minus back EMF divided RA. Okay. This is the quantity that we have as an average current flowing in these circuits. Let me just stress a little bit the consideration that was made at the beginning of the discussion, okay, that leads to these different cases. How it's possible to have a current flowing which is negative, okay, because the case B is for a negative current, so a current that flows entering the node A, not exiting, okay, the direction of the current is negative. So let's a little bit consider the direction of the current. Suppose that the direction of the current is positive, means that it flows from, say, the left to the right, exiting the node A, it means that according to our previous expression, this is the current IA, this is positive, okay? So this means that basically the voltage VAN should be higher than the back EMF. The voltage VAN is given by, which is the average voltage, DIA multiplied VD, which can be greater than EA. So basically the duty cycle should be higher than the ratio between EA and VD. So in order to have a positive current, say, the duty cycle should be higher than this ratio. Remember that the duty cycle is a quantity that should be greater than 0 and less than 1. Okay, so what does it mean? That according to this basic definition, it means that EA should be positive. Okay, because it is negative. If it is negative, it's not possible to have a duty cycle higher than a negative quantities. And that EA should be less than VD in order to be less than 1. Okay, so these are, say, the condition for having a duty cycle which is physically a physical meaning. So the duty cycle DAA should be basically, according to the description, less than 1 and higher than EA over VD. So this is the situation that should lead to having a positive current. Okay, so it means that if you have the, say, let me show graphically, the duty cycle that ranges from 0 to 1, okay, this is the duty cycle. When the duty cycle is, I don't know, it is the value EA over VD, but supposing that it is here, if you have that the duty cycle is in this range here, then I have a current that flows exiting from the node A, okay, and so in this sense, this is the positive current. What happens if you have if you have negative current, so IA average value less than 0, it means that VAN average minus IA over RA is negative, less than 0, so that VAN is less than EA. Again, the average value is DAVD less than EA, so DIA less than EA over VD. Again, the duty cycle is, say, something that goes from 0 to 1, so it means that the duty cycle should be higher than 0 and less than EA over VD. Okay, this is the situation that leads to have a negative current. And so, for example, if the duty cycle is in this interval, then the current average is null. So, this circuit has an intrinsic bidirectionality for the current. Okay, this is why it is called a bidirectional converter, because you can play with the unitary switching function, providing you specific duty cycle, DA, commanding the position of the switch. And according to what I'm saying here, you can have, say, a positive or negative current, say, flowing into the motors. Okay, so this is something that is bidirectional in current. By the way, okay, remember that VAN, which is exactly DA multiplied VD, is something cannot be negative, okay, because the AA is from 0 to 1, VD is positive, so VAN, average value, is something that ranges from 0 to VD. So I have at the output, at the current port of my switching power pole, an average voltage that can be only positive, so it is said to be not reversible. The voltage is just, say, positive one, but the current can be a bidirectional current. So I built a circuit in which basically if you put the average current here and the voltage VAN here, okay, you can have possibility to work into the first quadrant where the current is positive, or also in the fourth quadrant here, in which the current is negative. But the voltage VN is always positive. Okay, so this is a bidirectional converter, making possible to inverse the direction of the current. Is also called a two-quadrant, or 2Q for short, converter. Okay, these two-quadrant converters has the characteristic can change the direction of the current. Okay, it can exist, for example, two-quadrant converter in which the current is always positive, but the voltage is reversible. Okay, so in that situation you have again two-quadrant converter, but it's a reversible converter because the only thing you can have is the reversibility of the voltage. So according to our exercise, let me put in the first situation, in the A case, the current is 5 amp. And according to our previous circuits for DC quantities, VAN is EA plus RAIA. Okay, I have that this is 75 volt, RA is 0.5 multiplied 5 amp. And so this gives you 77.5 volt, which is answer the first question. The voltage averaged at the node AN is 77.5 volt. The duty cycle, let me put here an A because this is for question A. The duty cycle A is given by what? Is the average voltage divided VD. So this is 77.5 divided VD is 100 volt. So this is 0.775. Okay, so this answer the first question. Second part is the B. IA is negative 5 amp. So in the same way, we have that VAN average value is EA plus RA multiplied IA average. So 75 minus 0.5 amp. This is 72.5 volt. The duty cycle DAB is VAN B over VD, and this is 0.725. So basically we have this situation for the voltage VAN. The voltage VAN is this is my TS. A duty cycle is quite large. Remember, this is for the A situation, for example. So it is T on is duty cycle at the point A multiplied TS. So this is 0.775 multiplied TS. TS is the inverse of the frequency, so it is 1 over 20 kilohertz, so it's 50 microsecond, and this is 38.75 microsecond. Okay, this is 50 microsecond. In that situation, the duty cycle is exactly 0.775. The average value here, VAN average A, is 77.5 volt. Remember that here you have VD, which is 100 volt. This level here. Let me just have here to put the level of the back EMF EA, which is 70 is 75, so it is opposite to this one. Is here. Okay. 75 volt. As you can see, the average value of the voltage VIN is a little bit higher than the back EMF, and so it is the reason why you have a current, average current flowing toward the motor, okay, exiting the node A. What happens in the case B? In the case B, you have a duty cycle which is a little bit lower. TS is always 50 micro. T on in that situation, T on B is 0.725 multiply 50 micro, so it is 36.25 micro. Okay, and here you have an average value which is 72.5 volt, and this is less than the back EMF. Okay, in that situation, since the average value is less than the back EMF, the current, say, is directed towards the node A, starting from the motor. Okay, so graphically, the solution can be, the meaning of this computation can be also derived in this way. Just a consideration about the power flow that you have in these bidirectional circuits. You have this bipositional switch. This is the DC motor model. Okay, and this is the node N. Let's consider, say, this section, the section at the node AN, so the current port of our directional converter. And I know, because I explained it several times, that the voltage VIN do have here is always positive. Okay, it can be, say, large up to VD, but this is positive. While the current can be positive, the average current can be positive or negative. Suppose that I have a positive current flowing here, positive average current. So it means that I have a power flow that exits the switch power pole and it is provided to the motor. Okay, So the power is positive in this situation. Remember the definition that we can have according to the direction of the power flow in this kind of circuits. In this situation, I'm providing power to the motor, so I'm what is called the motoring operating mode. Okay, the power is provided by the motor, and the motor exploits itself. Okay, and this is called the motoring mode. So in that specific situation, you can see that, and this maybe with the number is clear here, okay, because this is the A situation. I have the average voltage that is higher than the back EMF, okay? So the average voltage you can have here is greater than 0, but in this specific case, in the case A, this is also higher than the back EMF EA. So the current can flow, say, from the left to the right. We are in a situation in which the power flow is provided by the bidirectional converter and it's exploited by the load. And if you think of this situation, you can recognize that this kind of motoring mode operation and this kind of power flow is the same you can have in a buck converter. In a buck converter, you have, let's say, the power flow that goes from the side in which you have the large voltage supply to the side in which you have the, say, the less voltage. Okay, is a step down converter. In a buck circuits or step down, the operation is something like this. The power flow is in this direction. You have a current flowing from the node A to the load. So the power flow is this direction because you are, say, converting an input voltage VD into an output voltage that has a value which is less than VD. Okay, and the power flow exactly has this, say, direction. This is the way. This is why these circuits that drive the motor in the motoring operating mode. Sometimes it's also called the buck mode. Okay, we are providing power. What happens when the current flows in the opposite direction? So what happens when the current is negative, the average current negative? EA, LA, RA, DC motor model, CD input capacitor, VD constant voltage. Supposing now that the current is, the average is negative, so at this direction, entering the node A, what about the power flow? But since the voltage here, VAN, is always positive, but now the current is entering, so the product of the two provides a power which, say, flow from the load to the source. Okay, in this direction. In this condition, you are no more in the motoring operating mode, but you are in the braking operating mode. This condition is basically similar to that you can find in a boost converter. In a boost converter, which is again the DC-DC converter, also called step up, okay, you have that low a voltage is converted into another DC voltage which has a value which is less than the input source. Okay, you are stepped down your input voltage. So in that condition, remember our example that we had previously, we have something like this. This is the load. This is our source. And in that situation, the power flow has exactly this say direction. Okay, the power transitate from the right to the left. Okay, from the current port to the voltage port, if you want. Exactly what happens here. So this is sometimes also called the boost operating mode. Braking or boost operating mode. So if you think about our quadrants, okay, in which you have average current and voltage at the current port, then you can operate in the first quadrant with both are positive. So this is the motoring or back operating mode, or you are in the braking or boost operating mode if you are operating in the fourth quadrant where the current is negative. Okay, so basically this is the how it is obtained, this bidirectionality of the current, and also it has an impact on the power flow direction. Okay, so now the second question is about what happens for just one of the two conditions. See, it was about the ripple of the current here. You can have in the case A. Okay, so only, this is number 2 question, only average current positive 5 amp. In that situation, the ripple of the current. The ripple of the current is the small undulation of the current flowing to the inductance, to the current that you have in the motor, that is superimposed onto the DC level. Okay, so we have a current IA that has a DC level, so the average value, which is exactly 5 amp in our example here. And then superimpose on this current, there is a fluctuation, which is the ripple. Okay, so the ripple basically is the AC components of the current IA. Okay, the average value is the DC quantity, this say level, this constant level, but superposed on this there is just say AC contribution. Remember what I said in defining the circuits here, that the current IA has a DC contribution, average value, and then you have say something which is just AC, and this is the ripple. So let's use for computing the ripple the circuits in which by the superposition principle I just consider AC contribution and no more the DC part. So let's consider AC quantities. So for doing this, I need to consider the AC contribution of the voltage VIN, RA, RA, and then I have not to consider the back EMF, but back EMF is constant, you are in a steady state, and so this is a DC quantity, and for our purposes here, we want to consider just the AC contribution I don't want to consider the back EMF. So the back EMF is null. This is the voltage A, this is the node A, this is the node N. This is the circuit I have to consider. Just to simplify a little bit this analysis, okay? The analysis can be, say, performed with exactly the circuits in which you have VAN, LA, RA, a stop. But just to consider, say, a first order approximation, let's compare the impedance at the frequency of switching, which is 20 kilohertz of our circuits. The impedance of the inductance LA is 2P LA multiply Fs, and this is 2P 20 kilohertz multiply is 1 millihenry. This is let's say more or less 126 ohm, and this impedance is very large with respect RA, which is 0.5 ohm. Okay, so if you consider that the switching frequency is 20 k. So as a first order approximation, let me neglect RA with respect to LA. Okay, so the circuit is becoming just the series of the AC component of the voltage VAN and the inductance LA. Okay, simplification. So with this hypothesis, the voltage VLA, so the voltage, this one across the inductance, is basically the same of the voltage AN, which is the AC contribution. Also remember that VLA is LA DIA over dt. So let me consider these expressions to plot the behavior of the inductor current, of the ripple of the inductor current. Here I want to plot VAN T, so this is the AC contribution, no more DC quantity. And this is something like this. Okay, this is TS. Remember, this is 50 microsecond. This is T on, 38.75 we computed before, if I remember well. This is just the AC contribution, okay? This is the AC part of VAN. So it is VAN to which I subtracted the average value. Okay, so this is VD minus VAN. VAN average value. And this is negative VAN average value. Okay, because this is what I need for computing the ripple. Let me just consider the ripple of the current flowing through the inductor. Okay, during T on, the voltage across the inductor is positive. Remember that I have VAN is L A the IA over the T. So in this 0 to T on interval, the voltage across the inductor is positive. And so it means that the I on the T is increasing, okay? I don't know, supposing that is something like this. The slope here is VD minus VAN over LA, positive. Then during the second part of the period TS, now the voltage is negative to negative VAN average value. So the I on the T experience a negative slope. We are in steady state, so the current at the end of the cycle should be the same as the current at the beginning of the cycle. Here the slope is negative VN average value over LA. So the current has this behavior, the AC contribution of the current, okay? This is again the AC part of IA of T. Again, this quantity has no DC component because just AC part. So if you want, this area here should be the same of the area you have here. The ripple is exactly this fluctuation you have in this quantity here. Let's compute the peak-to-peak ripple. So let's compute this quantity. Let me call IA peak-to-peak. In order to compute this ripple, we can take advantage of the slope we computed. Takes whatever you want, the positive or negative. Let's take the positive slope, for example, VD minus VN average value over LA. This is the slope you can have during the interval t on. So the slope multiplied the duration of the slope, and the slope is t on, so it is dA multiplied ts, gives you exactly IA peak to peak. Okay, I have the slope, I have the duration of the slope, I can get the peak to peak ripple. Now, VD minus VAN average value is DIA VT over LA DA difference. So this is also VD over LA, let me put FS instead of TS, DIA multiplied 1 minus DA. This is the ripple, IA, the ripple, the peak-to-peak ripple, okay? So this is the expression. Now we can put numbers. 100 volt, VD, 1 millihenry, 20 kilohertz. Duty cycle is 0. For the case A, which is the case we are interested, is 0.775, 1 minus 775. And this gives 0.872 amp. Okay, this is the peak-to-peak ripple. So it is exactly this quantity. This is 0.872 amp. And this answers the second question, which is the peak-to-peak ripple of the current. Okay, this is just the AC contribution. If you want to know, we want to visualize the behavior of the total voltage and currents at the current port of our converter, let's plot the total current, so DC plus AC contribution, and the total voltage. Okay, VAN is the average quantities plus the DC contribution. This I already drawn it before, something like this. 0 VD TS T on. For the current, you have IA, let's say contribution, which is the DC contribution. This contribution is 5 amp. Okay, and superimpose on this constant level, you have the the small ripple 0.872. So it's something like this. Etc. And this quantity here is the ripple 0.872. As you can see, the ripple is small in this condition. So our, say, consideration about the fact that the current flowing through the node A is more or less constant due to the presence of what is called the current port is basically validated. Okay, there is a small ripple which is superimposed. The small ripple is due to the several factors that are indicated here in this expression. Okay. For example, you can justify the presence of the ripple because you have a finite alley. If the alley inductance can be, say, larger than 1 millihenry, then you are able to reduce the ripple further on. Okay. This also depends on the switching frequency. Okay, if I increase the switching frequency, then it happens that my ripple, it can be reduced. Or if you can consider the ripple as a consequence of our demodulator. Remember the say description of the operating principle of any kind of switch power pole. Okay, that basically is a sort of a communication channel in which you have information that are, say, within the variation of a control voltage. Then you use this kind of information as a modulation signal in a modulator, and then you transfer your information content into the variation of a duty cycle, which trigger the operation of a switch power pole that produces a distortion in the voltage VAN, and you need to, say, demodulate this highly distorted signal in order to extract the information amplified that you have at the beginning of this channel. Okay, and the demodulator is a low-pass filter. The same action is here. Okay, the low-pass filter, the demodulator now is the LA-RA. So basically, it is composed by parameters, that quantities that are, say, due to the connected motors. It's not a specific demodulator low-pass filter inserted for the purpose of, say, extract the information I need. Is just I just exploit the low-pass filtering action due to the LA and RA. Okay, this is a low-pass filter. It's a first-order low-pass filter. Okay, let me just consider just this alternative view of the problems. Okay, I have a low-pass filter. Let me just consider which is the say the ratio, the transfer function of this low-pass filter. We have these circuits for AC variation, in which you have RA, RLA. The current here is the current IA. This is VAN. Okay. Just consider the Laplace domain, say, circuit. So let me to consider Laplace variables. So VAN S. The current is IAS, and then we have SLA. Okay? Just for the purpose to define the transfer function, is a linear circuit. We can use the Laplace domain, so we can find that IS is VIN over S multiplied 1 over RA plus SLI. So the transfer function between the current and the voltage basically is, well, we can also write in this way, 1 over array, extracting array 1 plus SLI RA. So there is if you draw the body plot of the magnitude, you can have IA over V and A over frequency. Then you have a pole here, which is FP 1 over 2P LA over RA. You can see this is a low-pass filtering action, okay? And this low-pass filtering action has a negative 20 dB decade. Okay, is a single pole filter, okay, that is exploited as the modulator. Okay, so FP, if you put numbers here, this is 1 over 2 P, 1 milli divided 0.5 ohm. This is more or less 18 hertz. Okay, this is 80. We are considering the ripple at the switching frequency of 20 kilohertz. So we are, say, in the region in which this filter is attenuating a little bit. Okay, let me consider that 20 kilohertz is here, just for say example here. So you have, as you can see, this attenuation. Okay, and in this sense, we can see that the ripple that you have on the current, okay, here, is the residual of the imperfect action of this low-pass filter. Okay, if the filter was ideal, okay, you have no, action, no contribution of a small ripple at the switching frequency. Okay, this ripple is due to the switching frequency action of my switch, and you can have a small residual of this ripple due to the imperfect action of this single pole low-pass filter. Okay, basically, if you increase the switching frequency, okay, you are able to increase this attenuation. Okay, but this is exactly the same results that I found out here. Increasing Fs, you can have small peak-to-peak ripple. Or maybe you can increase LA. If you increase LA, it means that you are changing the position of this pole, say moving to the left. And so basically you are, say, having a better filtering action. So it's reducing the pole. So the same consequence you can find out simply by looking at this equation for the ripple, the peak-to-peak ripple, basically can be justified in terms of the filtering action of the demodulator you have at the output of this, at the current port of this switching power pole. Okay, this is what we get. Basically, increasing LA helps to reduce the peak-to-peak ripple, or increasing the switching frequency helps to reduce this peak-to-peak ripple. Okay. Third questions that we have to answer, so question number 3, is about which is the maximum possible peak-to-peak ripple, because what I found here is basically the peak-to-peak ripple, okay, that I have for a specific duty cycle that I call A. Okay, duty cycle A is 0.775, the specific duty cycle that provides you 5 amp at the output. Okay, the question now is a little bit more general, because it asks which is, can we be that, since it varies with the duty cycle, you can have a maximum of this ripple. Okay, and to find out this ripple, let me again use the previous derived expression, which is Vd over LAFS, which is a constant quantity, and then you have now the generic duty cycle. Okay, in order to find out which is the maximum, of course, I have to take the derivative of the current ripple versus the duty cycle to put it equal to 0. Okay, and so this is Vd over LAFS, and then I have 1 dA minus dA square due dA equal to 0. Okay, so this dA is dA for which you can have the maximum ripple. So dA star is, you can find here 0, so it means 1F. So for the duty cycle, which is exactly 1F, you have the maximum. And so the peak-to-peak ripple, which is the maximum one for dA star 1F, this is VD over LA FS multiplied 4. Simply replace 1F in the previous expression, you can find these quantities. This quantity gives us with the number 100 volt for 1 millihenry, 20 kilohertz, and so this is 1.25 amp. Okay, so you can see that this is quite large because this is a not negligible fraction of the overall DC quantity, okay, which is 5 amp. So you find before. The previous expression of the peak-to-peak ripple can be also, say, graphically represented. Basically, the expression that I want to graphically represent is this one. Okay? Depends on the duty cycle. When the duty cycle is 1F, the cycle can range from 0 to 1. When the duty cycle is 1F, you get the maximum. And the maximum is VD over 4 LA multiply FS. In our example is 1.25 amp. Then I also find out which is the expression at 0.775. Remember, it's the 5 amp case. And this was 0.872 here. If you say, sorry, here, if you try to have all the points, it's easy to understand that this curve is sort of now the drawing is not perfect in my let me put this is 0.75, something like this. So this is what happens. Of course, when the duty cycle is 0 or when the duty cycle is 1, you get no ripple because, let's say, it is just a constant. The duty cycle or VAN average value is the same because this is simply duty cycle multiplied VD. So you can have here VD, you can have 0. Remember that VAN average value always ranges from 0 to VD. Okay, to VD and F, etc. Remember this quantity here, which is the maximum possible value, because we compare this quantity for the for other situations, for other topologies. Okay, have you questions about this this part? Have you understood the way I can get bidirectionality in the action, so motoring or braking mode into this bidirectional converter? Is clear? Okay, if you have no question, we can have a little 10 minutes break, okay, and then we can continue this topic later. Just to say, give you a little bit, say, insight in this curve I plotted here. This is the expression of the peak-to-peak ripple of the current. It's not the value of the DC quantity of the current. It's just the, say, AC component of the current superimposed onto the DC part. Okay, remember that, as I said previously, for duty cycle that are larger than 0.77, I have positive DC current. So here, the IA is positive, okay, in this small interval here. For all these other duty cycle less than 0.75 here, the current IA is negative, okay? So even if you have a negative AC current, you can have, say, a ripple on it, okay? This plot is just for illustrating you the ripple, okay? Here, the AC contribution, the AC here at this point for duty cycle 0.77, IA was 5 amp, okay? In that situation, the A average value is given by, let's say, it was VAN minus A over RA. And VAN here is VD divided by 2. So it is 50 minus 75 over RA, which is 0.5. So it is negative, of course, and is 25 over 0.5. So here the contribution of the DC current is, say, larger than 5 amp. You have negative 50 amp here. So even if you have this higher ripple here, also the DC quantity is, say, larger. Okay. So by the way, this plot is just for the value of the peak-to-peak ripple. Is not interested. Is not included the component, the DC component. Okay. So let's continue. Just this two-quadrant bidirectional converter in a more practical view. Okay, so let's see what is the practical implementation of the bidirectional is a bidirectional DC to DC converter. Up to now, we just illustrating some basic concept on the bipositional switch circuit, but how it can be implemented in practice. In practice, you can implement the bipositional switch, so the switch power pole, by having transistors. So suppose that this is the voltage port, which you have VD, and then you have the bipositional switch. Let me consider IGBT. There is no limit here. Okay, you can also consider MOSFET if you want. And let me put the circuit in this way. You have two switches. Okay, this is TA plus, TA minus, DA plus, DA minus. This is the node A, this is the node N, and then we have LA, RA, so the motor model. Okay. So I explained before that this converter is a two-quadrant converter, and it's bidirectional in the sense that the current flowing in the current port, so the current you can have here, is a bidirectional current flowing in exiting the node A for motoring operation, or say entering the node A, so reverting direction for braking operating mode. In order to manage the possibility to have bidirectional flow of the current, we need to implement the two switches that we need in the switching power pole by using bidirectional switches. So switches that are able to manage a current that can flow in both directions. Okay, this is the reason why I put diodes across the IGBTs. Okay, IGBTs is a switch that can only flow current flowing in this direction from the collector to the emitter, okay, when the device is on. When the device is off, the voltage that can be blocked, that can be supported, is just a voltage, say VCE, in this way when it is off, and this is the current when it is on. So basically, this is not a device that can manage bidirectionality of the current. In order to get bidirectionality, you have to add a diode, okay? And so if I put a diode in this way, so a diode connected between the collector and the emitter, then when the IGBT is on, it happens that the current can flow from the collector to the emitter. When the IGBT is off, so it is like an open circuit, then the current can flow through the diode in this way, making possible bidirectionality of the current flow. Okay, so I add this diode for getting bidirectionality of the current. Okay, if you want to consider the same behavior, just looking at the current I and the voltage V across, say, the output port of the IGBT, we can say that when the IGBT is off, the current flowing through it is null, and the voltage can be positive. Okay, this is when it is off. When the IGBT is on, we have a current flowing through the collector to the emitter, and so it is here. As you can see, this is a one-quadrant switch. Okay, since we need to build up a bidirectional converter, having the possibility to manage current flow in both directions, we need to implement the switching power pole using bidirectional switches. And the only way to get bidirectionality is to add the diode. With the diode on, then we acquire this other quadrant in which when the switch is off, but the diode is on. Okay, switch is off. So switch on, switch off, but diode on here. So we can get two quadrants. The same behavior, it can be obtained by MOSFETs. Okay, the difference, there are a couple of differences. The first one is that while in a GBT, this diode should be inserted by manufacturers, okay, specifically for the purpose, they have to, say, integrate on the same substrate where there is the IGBT, also the diode connected in this way. The MOSFET has the, say, the possibility, the characteristics that this diode is intrinsically included in the MOSFET itself. Okay, this diode here is the body diode. So the MOSFET is intrinsically a bidirectional device that is able to manage this, say, different direction of the current flowing through it by the body diode. There is another difference, is that when the MOSFET is on, it can be, it can have a current flow in this direction, drain and source, or it can have a current flowing this way. Because when a channel is formed into the semiconductor substrate, this channel can be the path for current in both directions. So when the MOSFET is off, the only way to have current flow is through the body diode. This is not happens for the IGBTs. Okay, the IGBT, when the IGBT is on, you can have only a current flow in this way. There is no possibility of current flowing from the emitter to the collector. Okay, in order to get this current here, you have to consider the presence of the diode. Okay, so pay attention to this difference. So basically here you have in this switch power pole 2 IGBT in a totem configuration, if you want. They are commanded by 2 signals, okay, here, that are, say, one the complementary of the other. So you have QA and then you have QA minus, which is 1 minus QA. And here you have your comparator with the triangular wafer and the control voltage. Okay, so the 2 switches are never on simultaneously. This is important. And I put the transistor and diode in this way because I want to highlight the behavior, let's say, of these 2 components and of these 2 components in my next explanation. Okay, so let me discuss a little bit this circuit. For example, considering 4 different situations. Basically, there are, say, 2 situations, but then we can mix up what happens in 4 different cases. The first one is the situation number 1, is this. Suppose that you have an average current which is positive, and the minimum and maximum current that are both positive. So this is the situation that I'm going to graphically describe. I have the VAN, so this is VAN, so both AC plus DC. I don't know the duty cycle, I just put, say, rectangular waveform without worrying about the correct value of the duty cycle here, okay? And then let me draw the current IA, again, both AC plus DC. So I have AI average value, which is positive. So it means that, for example, it's here. And then I have the minimum and maximum value of the instantaneous current, which is also positive. So I have something which is, let's say, something like this. Okay, so this is the IA maximum, IA minimum. They are both positive. So let's see what happens in our circuit with particular reference to understand which are the devices in the switching power pole that conducts the current. Okay, so this is TS, this is T on, which is also dA multiplied TS. Okay, this is VD, this is 0. So what happens when I have the voltage VIN, which is equals to VD? So what happens for the interval from 0 to T on? In that situation is the transistor TA plus, which is conducting. Okay, so I'm putting here the name of the transistor that are on, that they are, say, commanded to be on. So TA plus is on. Okay, if TA plus is on, since we are considering perfect action, TA minus is off. So this switch TA plus connect directly the voltage source VD to the node A. So VIN is VD. So during the time interval 0 T on, TA plus is on, so VIN is VD. In that situation, what happens? It happens that we have a voltage which is constant here. Okay, it is VD. We have this back EMF EA. We can have the same consideration that we employed later. For example, let me consider that, for example, VD is larger than AA. Okay. Also consider that AA is positive, so it means that the rotating speed omega m is positive, so the motor is rotating in a specific direction, I don't know, clockwise direction, for example. And so what happens here that it leads to having a current which is positive as an average value and a slope which is given by its positive slope giving up a rising current. Okay, so this directly comes from previous example. Okay, when we have VIN which is 0, it means that is TA minus which is on. TA minus is commanded to be on, TA plus is off. In that situation, the voltage VD is null. Okay, the voltage VD now is null here. And in that situation, what happens is that you have a negative slope across the inductance, etc. You have a negative slope here. So in this situation, which are the devices that are conducting the current? Okay, let me redraw here in a very small, or maybe let me put here a circuit that exactly depicts my discussion. Okay, here we have the transistor that is on. This is for 0 up to T on. So this device is on. This is a 1 here. So this is conducting. And then it happens that you have the current flow in this direction. So which is the device that conducts the current is the transistor TA plus. So here you can say that TA plus conducts the current. What happens in the interval from T on to TS? From T on to TS, Now the Ta plus transistor is off. Is the bottom transistor that it is on. The up transistor is open. Remember that the current is always positive, so the current flow in this direction. But this current cannot be conducted by the transistor. The current is directed, the current, sorry, is conducted by the diode. Okay, because the IGBT cannot make current flowing from the emitter to the collector. Okay, so this is not possible. So the current basically is conducted by the diode D B minus. Sorry, DA minus. So here is DA minus that conducts the current, and then the situation repeats itself with the same device. So among the 4 devices that are included in the switching power pole, for that specific situation, the device that always conducts the current are, depending on the section of the period, T on or say not T on, is TA plus, TA minus. So there are these devices that are in the blue box here. Now something will be easily recognized. Remember the buck. In the back you have basically here a switch, and then you have the diode. Okay, so during T on is the switch which is closed and make the current to be conducted, and then when the switch is open, there is the freewheeling phase in which the current is conducted by the diode. Okay, so this is exactly the behavior of the buck circuit. Okay, so these 2 components in the blue box exactly are the devices that you can employ for for building a buck DC-DC converter. Okay, and if you want, this is also the reason why in this situation, which you have average voltage VIN positive and average current positive, so it is a operation in the first quadrant. This is called motoring mode, but also buck operation mode. Okay, because this is exactly what a buck does. Okay, so transfer power from the side in which the supply is higher to the side in which the voltage is less, is a step down converter. Okay, so this is a buck operation. Okay, pay attention that if you have MOSFET, okay, in place here of the GBTs, then in this situation, so during this time interval, then the MOSFET can withstand a current flowing into the sense that is depicted by this current here. Okay, in the case you have MOSFET there, is the MOSFET itself that conducts both at the T-on period and in the other interval. Okay, it's always the MOSFET TA plus or TA minus. Okay, for the GBTs, TA plus, DA minus. Situation number 2. The situation number 2 is a situation that we have for let me see a moment here. Okay, is average current is always positive. The maximum current you have instantaneous value is positive, but the minimum current is negative. So now the situation is a little bit different. By the way, I forget to complete this plot. Let me just also draw here the current flowing at the input side, so the current IDA. Okay, the current IDA is the same of the IA current when the switch TA plus is on. So it is here. And it is null when TA plus is off, something like this. Okay. So let me just describe this second situation for the voltage VAN. Let me consider a generic rectangular waveform. For example, this one, T on, TS. The current IA. The current IA has an average value which is positive. For example, it can be here. But not all the instantaneous current is positive. Okay, for example, it can be something like this. Etc. Okay, as you can see, there is a part, a small, say, fraction of the overall period here, in which the current is negative. Okay, so from 0 to T star, and then the same happens for the other interval. So let's try to understand what happens for this situation. Remember that here you have TA plus on, and here you have TA minus on. Okay, so in this first section, you have for 0 T up to T star, that you have TA plus is on, but the current IA is negative. So we have this circuit here. T plus is on, so it is RA and A. So the current flows in this direction, in this interval. Okay, flows in this direction, and the transistor here is on. So what is the device that conducts the current? The current cannot be conducted by the transistor TA plus. Okay, cannot be conducted by transistor TA minus because it is off, and it can be conducted by the diode DA minus. So the only possible way is to be conducted by this diode here, which is called DB plus. Is DB plus? I think that sorry, this DA plus, but DB is, B is not considered that now. It's DA plus. Okay. So which is the device conducting is DA plus conducts. Okay. Now what happens? So this happens in this interval. What happens in the time interval between T star and T on? But the situation is that you have TA plus on, and then you have the current flowing, which is positive. So the situation here is exactly the same situation we analyzed here. No changes. TA plus on, current, which is positive. So here the device that conducts the current is A plus. Okay. What about the situation that lasts for, let me call T on to T double stars? Ta minus is on and the current is positive. So the situation is exactly the situation I have here. Ta minus is on and the current is positive. Is the device, is the diode Da minus that conducts the current. We have the same situation that I explained to you before. Now there is another segment here that I want to exploit, is the situation that has for, say, T star, T double stars up to Ts, in which Ta minus is on, but the current Ia is negative. In that situation, you have this transistor, which is called Ta minus, is on. So let me put a 1 here. EA, as usual, LA, RA. Ta plus is off, so I'm not considering it. Now the current is negative, so the current flows in this direction. This current can be conducted by the transistor. Okay, so now it is Ta minus that conducts the current, Ta minus, and then etc. We can replicate the behavior for all other periods. Okay, so now the situation is basically a little bit different from the situation I described before, because now there is also the conduction of Da plus and Ta minus. Okay, basically in that situation there is this kind of operating mode is called, sometimes is always a motoring mode, because the average current is positive, the voltage is positive, so the average power flow is from, let's say, the source to the DC motor. So it is a motoring mode. It's not a pure buck mode, because in the pure buck mode you have Ta plus, like here, and Ta minus operating like in this way. But basically, as you can see here, there is most of the time interval is exactly Ta plus Da minus. So this is called mainly buck operating mode, or motoring mode again. It's mainly buck because not a pure operating buck. There is also contribution from the conduction Da plus and Ta minus. Again here, which is the plot of the current flowing at the input side. So IDA, when Ta plus is on, it is similar to the current. It is the same as the current flowing to the current port. So it is here, something like this, and then it becomes 0 here. This is the second situation. There is another situation that we called free, in which now the average current is negative, but not all the current is negative. For example, EI minimum is negative, but IA maximum is positive. This situation is totally similar to the previous one, to the situation number 2. Okay, you have the standard rectangular waveform from 0 to Vt, T on, 0, Ts. Now the current has this behavior in which you have an average value which is negative. So this is average value. So we are in the breaking mode. Okay, we are just having an average power flow that is directed from the motor to the source, okay, from the right to the left. And then the current has this behavior here. Etc. So IA maximum is positive, but the minimum is negative this way, having average value. So again, here we can have 0, T star, in which the current is negative, T on, T double star, and TS. Okay, so we can replicate all the discussion we had before. TA plus, TA minus conducts in 2 different intervals. The device that conducts are TA plus here, when the current is negative, exactly as it happens in this interval here, TA plus, here in this small interval here. Then I have dA minus, and then we have TA minus. Okay, so the same behavior because it's the same situation. Now, as you can see here, a large part of the interval is TA plus and TA minus. But this situation is a situation you can find in a circuit that we call the boost. In a boost, you have something like this. This is the load, this is the capacitance. Okay, this is the circuit in which you have the switch here, and the diode is there. So it happens that when the switch is on, you have that the current flows exactly in this direction, so it is negative, so it's here. The A minus on, so it is here. And when it happens that the switch is off, so when TA minus is off, the current flows here toward TA plus, so it is here. So these 2 components are the components you must use if you want to derive a step up DC-DC converter. So it is exactly what's inside this purple box here. So I just separated the two kind of device just to highlight and to stress the presence of the buck and a boost converter into the same switching power pole. Here, as you can see, there is not only TA plus and TA minus that are working, because there is also the contribution of TA plus and TA minus, but basically most of the time are exactly in the boost operating mode. So we can say that this is the mainly boost operating mode. And of course, since the power transitates from the motor to the source side VD, this is a braking operating mode. Okay, the current is negative. And then there is the pure boost operating mode, which is the number 4, in which the current IA has an average value which is negative, and also all the instantaneous current is negative. So we have VAN 0 Vd T on Ts. The current IA is as an average value, which is this one, negative, and also the wall the current is negative. Okay. What happens here? But okay, the same discussion. TA plus is on, TA minus is on. The current is always negative. So what happens during TA plus? During TA plus, basically, this is on. But the current is flowing inside the switch power pole. So the current goes here. And the only way to make possible the current to flow is by the diode DA plus. So DA plus conducts the current. When it is the turn to TA minus to becomes on, okay, TA minus, the current is negative, and the current can be conducted by the TA minus. Okay, now we are exactly in what is called the boost operating mode, because the devices that conducts the current, depending on the conduction devices, let's say the on devices, are exactly that of the boost operating mode. Of course, we are again in the braking mode. Are there any questions about this behavior? About there is a difference, okay, in my discussion that will must be clear. Is the difference between the devices that are on and the devices that conducts the current. Not always devices that are on conducts the current. Okay, for example, in that slide here, in that page, TA plus is on, but TA plus is not the device that conducts the current. The current is conducted by DA plus, because the device itself cannot withstand a current flowing from the emitter to the collector. Okay, if you have the MOSFET can also conduct a current in that direction. Okay, when the MOSFET is on, it conducts. It's not the same for the IGBTs. There is a difference here. This must be understood. Okay, so this is what happened for the bidirectional converter and the way you can have, let's say, bidirectionality of the current flowing. Question, answer, problems? I want here to discuss a little bit an issue that someone of you asked me last week. What happens when two devices in the switching power pole, TA plus or TA minus, conduct simultaneously? And this is a very dangerous situation, because if you think how they are, say, the topology of the circuit, it is very dangerous, because you are shorting, basically you are shorting your supply. Okay, and when you are shorting your supply, means that all the currents flow without, say, very few limits, into the mesh that involves the supply and the two devices, easily inducing permanent failures, permanent damages, destruction of your circuit. Okay, so why it can be happen? It can be happen due basically to the delays you can have in the transistor turn on and turn off. As you may will know, and for students in mechatronics, this was discussed during the lecture, specifically devoted to the discussion of semiconductor devices, that the action of turn on or turn off a semiconductor real device is not immediate. Okay, when you command a device to be turned on, then there is a delay, and you have to wait to this delay in order to make this transistor to be effectively conducting the current, maybe on. When you command the device to be off, again, there is a delay from the instant at which you say, issue the target, the command, and the time instant at which the device is effectively off. So what does it mean in practical terms? That even if you set your command to be, say, at the same instant, for example, let me just discuss this graphically, okay? You have your modulator, remember my pulse width modulator. The modulator has, for example, a triangular waveform. Like this. So this is V triangular. We have this peak value. And then you have your control voltage. Since we are discussing DC to DC converter for DC motors, the control voltage is a constant, okay? V control A is a DC quantity. On the basis of this comparison, you can generate the unitary switching function. For example, here, QA is 1. And again here. Okay, what does it mean? QA is the signal that commands TA plus. So you have TA plus on, and here you have TA plus on. What happens to the unitary switching function QA minus? QA minus is 1 minus QA. And so this is something like this. 0. So here TA minus is on, TA minus is on. Okay, this is what I explained, say, my ideal case. So for example, here at this time instant, I command TA plus to, say, become an open sig, to switch off. So this is the turn off for TA plus, and simultaneously I have the turn on for TA minus. This happens in practical circuit. It happens that this turn off action is not instantaneous. So it leads, it has sometimes to get from TA plus to becomes effectively off. Okay, and the same happens for TA minus, because TA minus, the action of turn on of this device is not immediate. Okay, or for example, you can have the same situation here. Okay, when you are acting on turn on TA plus and turn off TA minus. Okay, so it can happen that, for example, if the turn on of TA minus is faster than the turn off of TA plus, it could happen that in this situation there is a small time interval in which both devices are on. effectively shorting the supply and inducing permanent damages, possibly leading to, say, replacement of your semiconductor components. Okay, this is due to the different delays you can have at turn on and turn off. So this situation is to avoid absolutely. You have to avoid. Let me just consider how this is typically managed. And in order to do this, I also need to write here the voltage VAN over T. VAN is VT when TA plus is on. So it is VT here, and it is 0 when TA minus is on. So it is something like this. Okay. So the standard solution for avoiding the cross conduction of both the transistor in the same switch power pole is to delay the turn on of devices. So what does it mean, delay? It means that, for example, you have the turn on of the device TA plus is here, okay, is here. I have to delay a little bit. So for example, I have to delay and to change the turn on time instant. Okay, I move the turn on from here to here. And the same happens for the other device, the TA minus device. I have to delay a little bit, so I change the turn on from here to here. So the standard solution is to delay turn on. Okay, in this way. What happens now? If I say have this situation, first of all, which is the amount of this delay? The amount is to delay is to be pretty sure that the device is, for example, here TA minus is completely off during the turn off time interval of the transistor TA plus. So it depends on the switching characteristic, the dynamic behavior of the transistor you are using. Okay, so this delay can be, let's say, let me call this delta T, and this delta T can be hundreds of nanoseconds, for example, or even larger, depending on the characteristic of the device. Okay, I prefer a situation in which both switches are left open than a situation in which both switches are, say, conducting simultaneously, of course. So basically, if I delay in this way, what happens? That I'm changing the situation in this way. Okay. This was the original time instant. And now I put this delay. Okay, so there will be a situation in which from TA plus to TA minus, for the time interval delta t, both switches are open. Okay, so now my question is that what happens when both switches are left open? Because up to now, this situation is not considered. Okay, let me consider what happens for two different situations. The first one is when the current IA is positive, and the second one will be when the current exiting the node A at the current port is negative. Okay, let's start with this positive current. So I comes from a situation in which there is TA plus on and TA minus off, from a situation in which both TA plus and TA minus are off. So what happens when TA plus and TA minus are both off? So let me just to consider the circuit. Okay. This is the switching power pole, CD, PD. You have TA plus and TA minus that are both off. So there is a small fraction of the period in which they are left open, okay? And then remember that I have the diode here. Okay, the current is positive. So the current, which is positive here, is conducted by which devices? We have DA plus, we have DA minus. The only device that can conduct this current is the diode DA minus. So the current flow in this direction. So DA minus becomes on. So what happens here? If DA minus here, it conducts the current DA minus. If DA minus is on, the voltage VAN is 0. So nothing changed with respect what happened before. There is the same situation. Okay, if I want to put here the new situation, nothing changes. Then TA minus becomes on, etc. Now, what happens here? Again, here we have the same situation. During this time interval delta t, both switches are left open in order to avoid cross-conduction. And so there is a small time interval, which is here, with both switches are, say, left open, the current is positive, so the same situation I described here also applied to that second interval in which DA minus is on, making the voltage VAN, so the voltage here, to be 0, okay? And so now here, the real situation is a little bit different because there is a, you can say, a difference in the output voltage, okay? So what does it mean that this difference in the output voltage? That I'm changing a little bit the average value. Remember that my useful quantity is the average value of the output voltage VAN. Now the waveform is a little bit different, so you have a difference in the average value, okay? If we plot the VAN ideal, ideal means with delta t equal to 0. We have something like this. Okay, 0 and VD. And compare with the situation in which VAN is, let's say, real. So with delta t equal different from 0. You have this edge is equal, but this edge now, the rising edge, is delayed by delta t. Let me put here the difference between the two. So the difference between VAN ideal minus VAN, let's say, real. The difference is in a small pulse. This small pulse has a duration delta t. By the way, delta t in the slide, I think that this is called t delta, but it's the same, t delta delta t. And this is VD, okay? So which is the difference in the average value of the voltage VAN that I have when I consider T delta or not considering T delta? I simply consider which is the average value of this quantity here, okay? If you consider this V epsilon averaged over one cycle, TS, this is the integral extended just on this T delta part, otherwise it will be 0. And so basically this is the area over TS, this VD multiplied T delta over Ts. Okay, so this is the difference that I have in the average value. It increases with the frequency. So if the frequency increases, the impact of this insertion of T delta is larger. It increases if I use a T delta which is larger. And so we have to consider this difference here. T delta, which is the time interval that I insert to delay the simultaneously action of these devices, is called the dead time, or blanking time, okay? This happens when the current is positive, and the same discussion can be done when the current is negative. What happens when the current is negative? So let me consider now the same situation as before. Okay, let me just a second. Okay, here. Let me go back to the previous situation, which is this one. Okay. I delay again the turn on. Okay, now I have a situation which both devices are, say, switching, are left open, but then the current is negative. So what happens when the current is negative and both devices are left open? The current is negative means that the current is entering here. Remember that the IGBT are, say, off, but the diode are still present there. And so the only device that can conduct the current is DA+. So DA+ can conduct the current, and so DA+ makes the voltage VAN that you have here to be equal to VD. So in this interval, the voltage now is VD. Instead of 0, as in the ideal situation, that you have VD. The same happens for the second time interval in which you applied at that time. And in this case, the situation is exactly as before. So the difference is here now. If you compare these two situations, the ideal one, VIN ideal without any dead time, and VIN real, so with the dead time, you have something like this. The same edges for the rising part, but the falling edge is delayed by T delta. So which is V epsilon, which is the difference. V epsilon is the difference between the ideal and the real. It's something like so it ranges negative VD here, and the duration is T delta. So Again, we can estimate the difference in the average value by averaging the V epsilon, and this is negative T delta Ts multiplied by T. Okay, now the difference is exactly this one. This can be also, this is also made in the slide. You can find in the slide. You have the control voltage here, and you have V AN. Okay, VAN ranges from 0 to VD, depending on the value of the control voltage. When the control voltage is 0, VAN is 0. When the control voltage is the same of the triangular peak value, this is VD. Okay, so in the ideal situation, the voltage VD, the average voltage VD. So this is exactly, remember, K pole multiplied V control A, where K pole is VD over the peak value of triangular voltage. Amplificator expression, we have an amplification. Okay, so this is the slope of this curve is exactly K pole. Okay, K pole is VD over V triangular peak value. So the slope of this curve. This is for T delta. So the dead time, the blanking time, which is null, the ideal situation. If you have a positive current flowing, then V epsilon is positive. So the error between the ideal and the real situation is positive. So this comes for T delta different from 0 and IA positive. While if you have a negative current, the V epsilon is negative, so it is upper the ideal situation. T delta different from 0 and IA. The difference here is exactly V epsilon. That way. Of course, I have this error, okay, because V epsilon is average value VD T delta Fs for positive current of negative VD T delta switching frequency for negative value, and I have to correct this value, okay, but this value can be corrected by the negative feedback, okay, so there is no so huge problem in a DC-DC converter, okay. Basically the feedback can recognize the difference in the average value and basically in the current flowing into the motor, okay, and then correct the duty cycle in order to get the same value you want as a target. Okay, so this error can be somewhere compensated. This error increases with the frequency and increases with T delta. So when you maybe are designing your own, say, switching power pole, and you have to choose T delta, be sure to take the T delta, the minimum T delta that make possible to avoid cross conduction of TA plus and TA minus without exaggerating too much, okay? Because you can have also stability problem, okay, if you exaggerate too much. The feedback cannot be, say, compensate the error. Anyway, we discussed these circuits, okay, for which is a two-quadrant converter, okay, two-quadrant DC converter for DC motor, making possible the bidirectionality of the current. Let me just draw these devices as it usually you can find in literature, datasheet, etc., which is something like this. DC motor model, okay. Okay, here are TA plus, TA minus, TA plus, TA plus, TA minus. This is node A, node N, etc. Okay, this is the circuit we analyzed before. Okay, I say just modify the position of the switches in the previous description here, just to highlight the presence of a buck and a boost. Okay, but basically, if you can find these circuits in literature, 2A plus is say drawn exactly up to the TA minus as I did here. This circuit has a name. Okay, the name is say half bridge or H bridge. Okay. Have you any questions about what I describe here? Something that is not very clear, that need other, say, explanation, whatever. Of course, this half bridge can be made, say, by also MOSFETs, okay, power MOSFETs. I use IGBT just to highlight the fact that when they are on, the current can be made bidirectional by the diode. Okay, this happens in the MOSFET just when they are off, because when the MOSFET is on, they can conduct current in both directions. Okay, guys, I prefer to stop here because the next topic will be the 4-quadrant DC-DC converter for DC motor. So a converter that is able to not only reverse the direction of the current IA, but also to make the voltage VIN to be reversible, okay, making positive and negative voltage. The 4-quadrant converter can be used for, say, applying operating point in all the 4 quadrants of the current and the voltage. Okay, this is the most general converter that you have. Okay, that is called. Sorry, this is. I'm sorry. This is not H bridge. So I'm just 3 hours. Is becoming too long. F bridge. Okay. The H bridge is exactly the 4-quadrant converter. So it's something that I will explain tomorrow. Okay. So if you have no questions, I can stop here. We can see each other tomorrow morning at 10 a.m. Okay. See you. Bye.